10.3 Hypothesis Test for a Population Mean. The objectives for this lesson is to test hypotheses about a mean, explain the difference between statistical significance and practical significance. There are three conditions that must be satisfied before testing a hypothesis regarding population proportion P. The sample is obtained by simple random sampling. Second condition, the sample comes from a population that is normally distributed with no outliers, or the sample size n is larger than or equal to 30. And the third condition is the sampled values are independent of each other. So this means that the sample size is no more than 5% of the population size. You can see the criteria right here on our overview sheet. We're under mean, that is a quantitative variable. Here, this is normality, this is independence, and the other one is randomly selected. So you can add that to the overview sheet if you would like. There are 5 steps for testing a hypothesis about a population mean mu. Here we have our two-tailed, a left-tailed, and a right-tailed. Notice that all the null hypotheses have equal. Two-tailed has not equal to symbol. Left has less than. Right has greater than. This symbol will always be mu if we're talking about means, and these two numbers will always match. Note that mu sub 0 is the assumed value of the population mean. That is, the first step is to write down your null and alternative hypothesis. Step 2 is select a level of confidence alpha, depending on the seriousness of making type 1 error. Step 3 is use number 13 on the calculator sheet to obtain the p-value and the test statistic. Step 4, if the p-value is less than alpha, we reject the null hypothesis, and if p-value is greater than alpha, we do not reject the null hypothesis. Step 5 is to state the conclusion. If we look at the overview sheet, you can see here number 13 is going to correspond to your hypothesis testing for one population. And here we have confidence interval would be number 11 if we're working with means. Let's look at an example. The mean height of American males is 69.5 inches. The height of the 44 male U.S. presidents, Washington through Trump, have a mean of 70.84 inches and a standard deviation of 2.73 inches. Treating the 44 presidents as a simple random sample, determine whether there is evidence to suggest that U.S. presidents are taller than the average American male. Use the alpha equaling 0.05 level of significance. Note, Grover Cleveland was elected to 2 non-consecutive terms, so technically there have been 45 presidents of the United States. So first, let's verify the conditions. First, was it randomly obtained? Yep. Second step, is it normally distributed? So n is equal to 44. That is greater than or equal to 30. So it is normally distributed. And then, is it 44 less than 5% of your population of males, American males? Yes, it is. Step 1 is to write your null and alternative hypotheses. So we're looking to determine are taller than the average American male. So we know we have to write equals for the null. Taller means greater than, and what was the average American male? 69.5 inches. And here's the keyword, the mean height. That's how we know mu. Step 2, your alpha. Alpha is 0.05. That's stated to you up in the example. Step 3, we're going to use number 13 on our calculator sheet. U sub 0, now that's what we just wrote down next to our null hypothesis and alternative. X bar, now we have our sample. So our sample is the president's, and that's 70.84. With a standard deviation of 2.73, and we had 44 of them, and we are doing taller than, so greater than. So our T, or our test statistic, is 3.256, and our p-value is 0.001. So our T was 3.256, and our p-value is 0.001. Step 4 is take our p-value and compare it to our alpha. That is less than our alpha. So when it's less than alpha, we reject the null hypothesis. When we reject, we say there is sufficient evidence. So step 5 is the conclusion. We can say there is sufficient evidence at the alpha equaling 0.05 level of significance to conclude the U.S. presidents are taller than the typical American male. Below is another paragraph of just some more in-depth explanation. The p-value of 0.0011 means that if the null hypothesis that mu equals 69.5 inches is true, we expect a sample mean of 70.84 inches or taller in about 1 out of 1,000 samples. The results we obtain are not consistent with the assumption that the mean height of this population is 69.5 inches. Put another way, because the p-value is less than the level of significance, we reject the null hypothesis. There is sufficient evidence at the alpha equaling 0.05 level of significance to conclude that U.S. presidents are taller than the typical American male. Okay, we have another example. The font size of Snickers bar is supposed to weigh 20 grams. Because the penalty for selling candy bars under their advertised weight is severe, the manufacturer calibrates the machine so that the mean weight is 20.1 grams. The quality control engineer at Mars, the Snickers manufacturer, is concerned about the calibration. He obtains a random sample of 11 candy bars, weighs them, and obtains the data below. Should the machine be shut down and calibrated? Because shutting down the plant is expensive, he decides to conduct the test at the alpha equaling 0.01 level of significance. So let's first verify the conditions. So was it random? Yes, it's random. Right here. Step 2, is it normal and does it have no outliers? Here our n, our sample size, is less than 30. So what we're going to need to do is we're going to need to go to number 11, and we're going to need to check for normality and outliers. So go to stat, edit. And now you're going to need to put the data points into the calculator. I'm going to pause my video and put these in. We now have the list or the data into list 1. We're going to second y equals, turn it on, select the last graph. Data list is list 1, hit graph. If you can't see anything, go to zoom, number 9. And then make sure our correlation is going to be greater than our critical value. Well, our critical value, n is equal to 11. So our critical value is 0.923. Our correlation is 0.930. This was covered in chapter 7.3. Your homework will give you the correlation value. You're just going to have to compare it to the critical value. If you do want to figure out or know how I figured this out, this will be attached to the page on the stock video page on Canvas for chapter 10. So this is greater than the critical value. So when that happens, we know it is normally distributed. And then we need to look for outliers. So we'll make our box plot, and that's going to be the 4th graph. You can see there are no points outside, so there are no outliers. So we can say this is n is less than 30, but is normally distributed, and no outliers. And we can say that 11 is less than 5% of all the Snicker bars. Okay, so the first step is coming up with our null in our alternative hypothesis. Our mu sub 0 is going to be 20.1. Now the alternative is a little bit more challenging. What you're going to want to do is look at the question. Do not make assumptions about what is stated up here, because if you do, you're going to say, oh, let's do less than. Maybe some might think let's do greater than. What you want to do is look at the question. It says, should the machine be shut down and calibrated? It's not saying there's more than this or less than this. It's just saying that. So when it's not clear, you're right, not equal to. Step 2, level of significance is 0.01, up from the example. And then step 3 is to figure out the test statistic and the p-value. We had data, so you can put it over to data. Otherwise, I believe it fills it in for you. Actually, it does not, because here we have 11 Snicker bars. So I go to data. We are looking at 20.1. It's in list 1, not equal to, and enter. So 1.041, p-value of 0.323. Be careful, if your p-value is larger than 1, at the very end there's going to be an e to the negative number. What that negative number is, so say this is e to the negative 8, you're going to move this decimal 8 spots to the left. So be careful when you see that. Remember, p-value represents probability. You cannot have a probability greater than 1. So when you see that, make sure, when you see a p-value greater than 1, make sure you look to the right to see if there's that e to the negative number there. T sub 0 is 1.041. And our p-value 0.3226. So compare our p-value to alpha. It is larger than alpha. So that means we do not reject the null hypothesis. Step 5, state a conclusion. When we do not reject, we say there is not sufficient evidence at the alpha equaling 0.01 level of significance to conclude that the Snickers have a mean weight different from 20.1 grams. So the first example was when n was greater than 30. This is the example when n is less than 30. This next example will be about practical significance. But before we move on, let's read the overview of this example that we just did. The p-value of 0.323 means that if the null hypothesis that mu equals 20.1 grams is true, we expect 32 out of 100 samples to result in a sample mean as extreme as or more extreme than the one obtained. The results we obtained are consistent with the assumption that the mean weight is 20.1 grams. In other words, the results obtained are not unusual under the assumption that the mean weight is 20.1 grams. So we do not reject the null hypothesis that mu is equal to 20.1 grams. There is not sufficient evidence at the alpha equaling 0.01 level of significance to conclude that the Snickers bars have a mean weight different from 20.1 grams at the alpha equaling 0.01 level of significance. The machine should not be shut down. It is important to understand that we are not concluding the mean weight of Snickers bars is 20.1 grams. We are saying we don't have enough evidence to say the mean weight is different from 20.1 grams. Remember, in hypothesis testing, we never accept the statement in a null hypothesis. We only say whether there is enough sample evidence to reject the statement in the null hypothesis.